Hello everyone, welcome to the last session of D&F block elements. In this session, we will be talking about actinoids and its property. Let's begin. So, talking about actinoids, actinoids are the elements which are following actinum. These are the 14 elements starting from thorium to lawrencium. Okay. The actinoids are radioactive elements. Okay. So, some of them they have half-life which can be from 1 day to 3 minutes. Okay. So, it's actually very difficult to study them. Okay. And another difficulty is some of them can be prepared only in nanogram quantities, that is 10 raised to power minus 9 grams, so which is very small to study them. Now their electronic configuration, you can note down that all of them they have 7s2 electronic configuration but variable occupancy of electrons in 5f and 6d subshells. Note that they have a lot of irregularities as well. The irregularities in the electronic configuration, it comes due to the more stability or relatively more stable half filled and fully filled f orbitals. Also, very important point, the 14 electrons are formally added to 5f. Okay, but not in thorium, but after uh, from Pa, that is the next element. Okay, from there we see the electrons are entering in 5f orbital, and it is completed at element at 103. Let me show it to you. You can see at actinium and thorium there are no 5f electrons, but the first electron comes at 91 atomic number and it fills up by 103. So this is the general electronic configuration you can see, and everyone is having 7s2. 7s2 is everywhere present, you can see, and variable occupancy in 5f and 6d orbital subshell. This is the electronic configuration in M3 plus, that is metal, in third after losing 3 electrons. M4 plus, which is another oxidation state. Trend in the radii, you can notice M3 plus radii are actually decreasing along the series. Same M4 plus, you can see that the radii are decreasing. Now this decrease in radii can be contributed or attributed towards actinoid contraction, which is due to the poor shielding effect of 5f electrons. So gradual decrease in the atomic size and M3 plus ionic size is actinoid contraction, exactly the same way how we studied lanthanoid contraction. Now the contraction is greater from element to element in this series. Why? Because of the poor shielding effect of 5f electron. Remember that in lanthanoid contraction the poor shielding effect was due to 4f electron, whereas in actinoid it's 5f electron, which are actually much more poor in shielding. Next, oxidation state. So you can see oxidation state, the most common oxidation state or general oxidation state is +3. Okay, and we have studied that they exhibit variable oxidation state, that is +3 and +4. Okay, but still the +3 and +4 they tend to hydrolyze. Okay, so basically we do not still consider the results from oxidation states only. Basically, it is kind of unsatisfactory to review their chemistry in terms of oxidation states. We will not study their oxidation state part. Now, also note that the elements in the first half of the series, they exhibit higher oxidation state. So let me show it to you. What do I mean by this? You can see this is your actinoid series. This is the first half of the series. Can you see that they are showing up to +7 oxidation state? Whereas the higher members they are only showing one oxidation state, that is +3. Also note that in this you see that +3 is the most common oxidation state. Okay, so oxidation states of actinum and actinoids. Now general characteristics and comparison with lanthanoids. So note down, first point, actinoid metals are all silvery white in appearance. They display variety of structure. The structural variability is actually obtained due to irregularities in the metallic radius, which are actually far greater than the lanthanoid. Next point. Important. The actinoids are highly reactive metals, especially when finely divided, because when you divide them, the surface area increases, hence the reactivity goes up. Also, the last electron which is there, it is in 5f orbital, which is actually very easy to remove. So hence they have high reactivity. Note that hydrochloric acid attacks all metals, okay, but most are slightly affected by nitric acid. So, very important. Why? Because they form a protective oxide layer. Okay, so this could be an exam question. Alkalis have no action on actinoids. Next, the magnetic property of actinoids are even more complex than those of lanthanoid. Why? Because we have 6d orbital, we have 5f orbital, so it's actually very complicated. So although the variation in magnetic susceptibility of the actinoid is roughly parallel to the corresponding result from lanthanoid. So how we have seen that lanthanoids, the increasing trend of magnetic property, that is it goes paramagnetic, and then again the paramagnetic nature decreases. So the lanthanides have higher values. Then the ionization enthalpy of the early actinides are lower than those of early lanthanoid, obviously because of 5f electron are more effectively shielded from the nuclear charge as compared to 4f electrons of the corresponding lanthanoid. Okay, so just make a note of this. So because of the outer electrons are less firmly held, they are available for bonding in actinoid. Just make a note of all this, go through all these points. Lastly, some of the applications of D and F block elements. We have seen most of them. Can be used in construction, iron and steel. We know MnO2 is used in dry battery cells. The use of zinc, nickel, cadmium in battery industry. We have seen that they are catalyst almost everywhere in organic and inorganic chemistry. Also, if you see in photographic industry, we use light sensitive material, AGBR. These are very broad applications, and that's it. The chapter is over.